Well, now we're on night 3.4 and we have two concepts left to introduce. That's unit vectors and tilted axes. Let's start with unit vectors. Here I'm going to draw my standard coordinate system with x to the right and y up. And now I'm going to introduce a concept, an abstract concept. I'm going to introduce the idea of a little vector that points along the x-axis, and I'm going to call that little vector I hat. Now this little vector is going to have a strange property. It is going to have length 1. So the length of I hat is 1. And I'm going to do the exact same thing with a second vector that points along the y-axis. So there's a little vector that I'm going to call j hat that points along the y-axis. And the length of j hat is going to be 1. Okay, now I'm not saying 1 centimeter or 1 meter or 1 inch or 1 foot. It's just got length 1. It's abstract. So actually, if x is in meters and y is in meters, this doesn't even really belong on the same picture because this doesn't have the same units. It doesn't have any units. It's just length 1. Now let's draw the vector, let's say some vector a on here. Okay, and I'm going to cast the shadow of a down on the x-axis. And this here is a sub x. That is a length that's belongs on this diagram. If this diagram is all in meters, then this a sub x is in meters. So that makes some sense. Now this though here is very abstract. It's just something that points in that direction. But now here's the cool thing. Using vector multiplication, I can make a vector that points from here to here. Okay, and what vector is that? It's the vector a sub x times I hat. Because you'll surely agree with me that I hat points right, and therefore a sub x, which is a scalar, times I hat, here it's a positive scalar, that's something that points to the right. And if this had a length 1, which is a pure number, and then this has, say, I'll actually measure it out, looks like about 37 centimeters, then 37 centimeters times this thing, which has length 1, has length 37 centimeters. So this thing here, what we've learned is that this vector that I've just drawn here is a sub x times I hat. Similarly, this vector, which goes from here up to here, this is a vector which has length a sub y and is multiplied by j hat. So, okay, this is a vector, which is this scalar times this unit vector. That's a nice representation of that vector. And now if I take this vector here and recopy it over to here, so I'm going to take this vector, a sub x times I hat, I'm going to recopy it over to here. We see that a sub y times j hat plus a sub x times I hat added together makes a. Okay, so here's our new thing. A is equal to a sub x times I hat plus a sub y times j hat. These are little hats. They're sort of like, they're also called caret signs, okay? And they're what we put over unit vectors. Now, that might seem kind of, I don't know, useless, maybe. It's just notation. It was fine if we said that AX is the vector that has components AX and AY. But this is another way of expressing a in terms of those components. Sometimes you just put parens around them and write out the components, but sometimes you do it like this. Okay, on to the final topic of the chapter, which is tilted axes. Here's a skier going down a hill. Now, you can certainly solve a problem of a skier going down a hill by laying down the usual axes, x and y. But this problem, you might sense, could get a load simpler if you lay down your axes like this. Okay, so now this is the y-axis, and the fact that the skier isn't jumping up off the hill or burrowing into the hillside is just a statement that y equals 0 for the skier's path. And then this becomes just a problem where x of t is the only thing varying. Okay, so if this is the x-axis, it looks like x of t is getting smaller and smaller if the skier is skiing that way. So this is a pretty good example of when you might want to introduce tilted axes to simplify a problem. Now, I don't know, maybe there's a seagull up here, okay? So I'm putting a seagull in the picture. And maybe there's someone here at the origin who's watching this whole situation. Now this person that's watching the whole situation says that, and is using this coordinate system, says that the seagull is up here. Actually, the seagull's up there no matter what, and this is the observer, and this is the seagull. But if the person here wants to describe the seagull in terms of these coordinates, we've now got an issue, which is that these coordinates are tilted. We have to be very careful. You don't anymore drop the thing vertically. Remember, I said it was kind of careful to say you drop the components perpendicular to the axis. Okay, so if this is vector s for seagull, then this is s of x, and this here is s of y. And in this coordinate system, I hat points that way, and j hat points that way. So those are the rules for how to deal with tilted axes. It can actually get fairly complicated to deal with tilted axes, but it's convenient and important, and we'll practice it, and hopefully you'll get good at it. That's the end of chapter 3.